Hello and welcome to another Diabatix webinar. My name is Adrian Kramer. I'm one of the application engineers and I have the pleasure of being your host for today's webinar. Today we want to talk about custom heatsink design for air-cooled lighting fixtures with either natural or forced convection. So today we're focusing on the LED and lighting industry and basically showing you how our thermal topology optimization can be applied to optimize for either natural or forced convection heat sinks. All right, to give you a little bit of an outline for the content that I have planned for you today, first we will dive into the natural convection use case that I have prepared for you. There I would like to show you two key things. For one, how to establish a thermal resistance network in ColdStream, and secondly, how to set up a ColdStream custom design start to finish. When we say custom design, we mean thermal topology optimization. And then in the second application that I've prepared for you, it will be a forced convection LED heatsink. And there I actually also have a reference design to which I will be comparing our ColdStream redesign to see what kind of performance gains thermally you couldn't achieve if you were to adopt thermal topology optimization to your workflow. Lastly, I'll sum up with the benefits of thermal generative design. We'll have some room for some questions at the end. There are also some moderators following along in the chat today, so please feel free to already drop any questions that you might have along the way, and of course we'll make sure that all of those get answered. At the very end, I'll leave you with some information on how you can actually discover ColdStream already today. Fantastic. So to introduce the two applications that we will be discussing today, firstly, we have the lighting fixture that will be cooled with natural convection. There we found a nice application online that we will use as inspiration, and we essentially redesigned what the heatsink on that can look like using our software ColdStream. Secondly, we have a forced convection application. Here we actually have a fan sitting on top of both the LED and the heatsink that drives the airflow to cool the LED, and we will show you how you can also optimize for both of these types of heatsinks. Fantastic. To introduce ColdStream a little bit more before diving into those two applications in detail, first, I want to really outline what makes us so novel. And so let's take the example that you're a thermal designer or a designer, and today you get a certain design challenge of optimizing a heatsink. Well, most engineers to this day are still stuck in this conventional design cycle. Simply put, it is a trial and error method of making CAD models, seeing in CFD simulation how they perform, and it's an iterative trial and error process that simply has human limitations to it. Well, where ColdStream can come in and help is through adopting a generative design cycle, meaning that if you have a certain design challenge, the role of the designer is only to define it as such, say what performance criteria are crucial, be it thermally or for the airflow. And with this good input data, you can achieve a generative design that is then a far more optimized solution. Because in fact, the way that ColdStream works is for a given design challenge where you would like to perform thermal topology optimization, our software will iterate through hundreds of design cycles. Each single one will have a full CFD simulation attached to it, checking the performance of that design iteration. And then we have our special algorithms that will adjust the structures such that the next iteration is hopefully better than the previous one. At the end of it all, you get an optimized solution because simply ColdStream can iterate through hundreds of designs in a much faster time frame than a human engineer could with this conventional design cycle. And so if you're maybe not familiar with thermal topology optimization, I've prepared a short video to actually see our optimizer in action. This is on a slightly different use case. It is still air-cooled with natural convection, but simply the heat source here is slightly different. This is for a PCB board. In the LED and lighting industry, of course, that would be our LEDs. But the principle is the same, that if you if you specify a certain design volume, telling our optimizer this is where you have the freedom to perform the topology optimization, what will happen is ColdStream will cycle through hundreds of different designs that are going quite fast here in the video, each single step of the way with a full CFD simulation to check how the performance is as we're approaching a thermal optimum. And in this entire process, we actually also take manufacturability into account. So one of the biggest added values that ColdStream can provide is that we link manufacturability to the start of any design process, be it you need a milled or an extruded heatsink or a 3D printed heatsink. ColdStream can adapt to the manufacturing capabilities that you have at your disposal, but also the ones that are simply the most cost-effective ones. If you have a very large volume size of your series production, of course, it doesn't always make sense to 3D print units. So we have a solution for both of those situations. And so before switching to the software to show you how we can do this thermal topology optimization, first want to highlight how a case setup works in our software. So the starting point is always uploading a CAD geometry. So we are a generative design software. However, design software doesn't in this case imply that we are a CAD tool. Rather, you prepare your CAD geometry and upload it to ColdStream. ColdStream will adapt to any complexity of shape that you have, whether it's cylindrical, rectangular, asymmetric, no problem for us at all. And then the first few steps are maybe quite familiar to you. Just setting a solid and a fluid material selection, setting the thermal and flow boundary conditions, and then of course we need to set certain targets and define where is my design space where ColdStream can optimize the structure. So in our targets we can, for example, say we would like to maximize heat transfer. Maybe temperature uniformity is really important. Perhaps you have certain restrictions on your pressure drop, or you need a really lightweight solution. We have over 20 plus targets built into ColdStream to help you find the exact multi-objective optimization that you need to simply get the most out of your heatsink and to simply not let thermal performance slow down the performance of your entire fixture. And so what do you get at the end out of it? And here's already a little sneak peek of one of the cases that we ran. Well, you get a step file of the optimized heatsink. And for us, step files is quite important. As I mentioned, we link ColdStream to manufacturing, and therefore we deliver step files and not just STLs. All right, I will now be switching over to the platform. Perfect. And so welcome to ColdStream. What you will see here is the projects tab. This is always the home page, and it's simply a file browser of all the different applications that you may be investigating. I will start us off with the natural convection case, which is right here. When you click into a project folder, first I want to highlight the different case types that we have. So of course you can make as many cases as you want for different engineering problems. The case types directly reflect our capabilities. So custom designing is the thermal topology optimization that we're famous for. Then of course we have a CFD engine built into ColdStream, so you can also perform simulations of that. For example, you could simulate the existing performance of the current heatsink that you have in your LED while launching a thermal topology optimization case in parallel, and then actually compare the performance of both of those in the same tool. There is a third case type which I will illustrate here, and this is what we call standard design, and it's essentially parametric optimization in case you just need a heatsink that is of a standard fin or pin arrangement, basically an off-the-shelf heatsink, and you need a parametric optimization for that. Great, so I will now dive into how to set up a case, because this really only takes a few minutes. So the only slight learning curve with ColdStream that I see with new users is how to prepare the CAD model slightly. For example, we need an air volume to define the case in ColdStream. We need to define where is the design space that is allowable for the topology optimization. But just with some slight tweaks in CAD, you can have access to thermal topology optimization with just a few clicks. So the steps to set up a full case go as follows: solids and fluids, boundary conditions, design space, and targets. So I'll run you through those. So the first parent region is actually already the LED lights, which is also our heat source. There the selection is simply, is it a solid or a fluid? Of course, you can rename it and then give it a certain material selection. So there we have a predefined materials library. If you need to make your own custom ones, it's as easy as filling out this information, and then it's always in your user library. In fact, we would like to model the effects of radiation, and in ColdStream, enabling that is as easy as a click of a button. And then with every solid, you can enable a heat source. And since we're on the LED lights, this information was already filled out, and simply we grouped all of the LEDs into one to not repeat that step too often, and then you just sum the total power that should be dissipated equally across all of the LEDs. Fantastic. The second step, or the second solid, is then just the fixing plate. So there the options are even easier. Just with a selection of a material choice, it's already defined, and the rest is left empty because it was simply not required or relevant information. And then the same with the glass. There we of course want to model radiation, and then the wall fixture that holds it all together. Then I already mentioned we also have to model the fluid section. So this volume would then be simply defined here as fluid instead of solid. You give that a material selection. So there we're in our fluids library. And of course, today we're focusing on air-cooled applications, but just to let you know, ColdStream will also adapt to any liquid-cooled applications. If it's water glycol, oil, you name it. Again, you can make your own custom ones. And even for two-phase cooling with evaporation, we can address that as well. So very important for natural convection is to make sure the buoyancy field is enabled. They're just the standard reference values, and you pick a corresponding gravitational vector. Here the y-axis is yellow, and therefore it's in the negative y. Of course, we want to pick a certain turbulence model. There we give you the freedom of selecting which one you would like. K omega SST is a good catch-all for any situation, so we applied it there. And then again, modeling the effects of radiation. Great, so the parent regions are all defined. Now let's define the boundary conditions. So the thermal one we already defined here. And for the flow boundary conditions, we have to define just the 6 sides of our air volume. And so in fact, for natural convection, what we will do is we'll define all the pressure inlets except for one side. Then the top is a pressure outlet. But as you might notice already, the pressure everywhere is 0. We just need to indicate at least one outlet. The rest is inlets, but essentially the information is the same. And what's important is that simply the pressure is 0 everywhere. Just to let you know, alternatively, of course, we can impose a fixed flow rate inlet, but you can actually also work with pumps and fans in case you have that driving the flow. Great, and then defining the design region. So basically the previous heatsink had a heatsink on the sides of it. We wanted to give the application a little more freedom in how much material can be added. So this is the design space that we defined. And here what's very important is selecting the manufacturing type, because like I mentioned, we guarantee fully manufacturable heat sinks. How can we do that? Well, you as the user have to give us the input information on what is actually capable with your tooling, with your supplier. And here are the main options that we offer: CNC milling, 3D printing, die casting, and sheet metal forming. So of course 3D printing was then selected with the specific parameters of what is then capable. So they're very important is the printing resolution, but we also actually offer a few additional 3D printing constraints, such as an overhang angle, if support structures need to be added, what thickness should those have, and if you allow for any unsupported structures, what is the maximum length that those should be. So if you parameterize the printing, 3D printing option, that is the main setting for the design region. And then simply you say, well, is the solid structure going to be like added to a certain section? And in this case, it is then the fixing plate, which we see here. Lastly, it is then just a material selection of what the 3D print job should be with. So in this case, then aluminum. Great. The last thing to do is to define that target. And you actually have a nice visual cue with ColdStream where this target is with this red icon here. And so there, the targets are always set at the bottom. And in this case, all of those were pertaining to thermal requirements. So of course, when we say maximizing heat transfer in ColdStream, we impose that through a temperature minimization across the heat source. But as you can already see, ColdStream can easily do multi-objective optimizations, and you can even apply different weightings. And so for every minimization objective, we have a corresponding constraint. So if you have certain maximum caps or minimum caps that are restrictions for your design, those are available too. Fantastic. So if this is constrained, you can submit the case to ColdStream for the optimization. And so, of course, we already ran this case. So what I would like to show you now are actually the results of this finished case. And so there today, I actually also want to highlight one of the just extra features that we offer within ColdStream, and it's what we call a thermal network. So actually, whenever you upload a CAD geometry to ColdStream, thermal interfaces between any of the parent regions that touch and the remaining boundaries, they're created automatically. So for example, here we see the fluid as the parent with all the boundary conditions. And what we actually can do quite nicely is trace from the heat source, how does the heat dissipate through the entire application. And on the side view here, we have the thermal resistances of that of the final application. And so, for example, the main heat source is then here, again highlighted with that 142.5 watts. You can then actually see how much heat is removed on every arrow. So it's a very nice way to actually see how the heat moves throughout the entire part. Let's say you have an application, for example, with a lot of small little parts, with 100 of different parts, you can actually have a nice thermal network here. What's also great is that with this thermal resistance value, you can actually use this to get a quick feeling for what happens if my source input for the heat source, if that changes, how does that have an effect on the resulting temperature? Now that you have all of this information, you can actually use that ratio to get a quick feeling for how a change in the heat source, in the heating power, will impact the final temperature. So that's actually a really nice way to have a quick overview on that. All right, so of course I want to focus on some 3D results. So I will highlight these next. All right, of course, we also want to show you some results in 3D. So what I've loaded up already is actually the final heatsink design. What you can see here with our 3D printing setting, ColdStream can actually make very organic looking structures to aid with the heat transfer. And so here you can not only see the heatsink that was generated, but you can actually give this also a temperature gradient, for example. You can enable some streamlines, of course, with, in this case we have natural convection. And in the end, what's very important are these final buttons over here, because this is where you actually can download the final step file and the results of the last CFD iteration. So all of this can be done in a very convenient post-processing, and the step file will be a smooth surface of the design that we see here. Our processor basically shows the mesh that we, by the way, also automate, but the final step file is a smooth surface file. Moving on to the second application I've prepared for today, the forced convection heatsink, which I can show you in this folder right here. So for this application, we have both an existing heatsink that is currently on the market that we have modeled in CAD and actually done a thermal simulation of. In addition, we've then launched a custom design, so a thermal topology optimization case in ColdStream, where we redesign the heatsink with an equivalent amount of design space available as from the reference design. So I will show you both the results of the finished simulation, then of course what ColdStream delivered for the custom design, and how to compare the both. So switching over tabs to the finished simulation, we see here the reference heatsink that we took as the starting point of this analysis. So on this application, we ran a CFD simulation where of course you then can see the thermal behavior and the results. For example, if you wanted to color, if you wanted to have a temperature gradient moving across the heatsink, you can do that, as well as having the results in the form of a thermal network or of tabular data. So then we wanted to redesign this heatsink, and so now switching over to the creation case of the custom design. Essentially here, this green volume is then the design space. We simply replaced the existing heatsink and included a new design space for ColdStream to do the topology optimization. There it was also on a 3D printing setting, and the only target in this case was a temperature minimization. So switching tabs once more, here you then see the finished custom design, and this is in fact the heatsink that ColdStream generated. So to dive a little bit deeper into the structures that ColdStream created, while on this side where the heat source is, you actually see these thick fins. On the back side, the design actually reveals that throughout this width you have additional skinny fins, and in fact you have the fan which was assigned as a fan outlet on this side. So in this case we have force flow, where the fan is a fan outlet sucking the airflow through this. And so while maybe on a first glance these thick fins seem like a counterintuitive design in terms of thermal performance, the combination of having these thick fins with these skinny fins close to the fan outlet, those in combination actually made for a heatsink that performs better than the conventional design I showed you in the simulation. The reason being is simply, you can see quite nicely here that this design creates these thin slits, and actually you create a higher effective contact area between air and solid, which of course aids with the heat transfer. In addition, because these air passageways are so narrow, it actually made the air velocity of the airflow higher, which also helps with the performance of the heat transfer. So those two things in combination made for a better performing heatsink. Of course, what is very interesting to see is that even on a 3D printing setting, such a design is trending towards something that could be extruded. So in fact, what we could do is potentially split this heatsink up in two halves, and then you almost have two standard heatsinks that could be easily manufacturable with extrusion. So it's very interesting when ColdStream has all the freedom to design with 3D printing, it makes something that could even be extruded. So again, as a reminder, ColdStream has some convenient post-processing. You could, for example, enable a temperature gradient here. Look at that. And we could, for example, enable the streamlines to see what is the velocity of the airflow, of course, with the fan sitting right here. And all of this we also have in tabular format, which you can see right here. So you will always have the average temperature, the maximum, average, and minimum temperature. A few other results down here, for example, pressure and flow rate. And in fact, what I think is really nice is ColdStream actually has a comparison view. So let's say we wanted to compare the performance of the simulation, so of the existing heatsink, with the custom design. And this is actually how all I see a trend that a lot of new ColdStream users, they start with this way, that they first want to simulate a design they already have, and in parallel launch a custom design to optimize the topology more thermally. Well, ColdStream can actually compare the performance quite nicely. If you add them to this comparison view, it populates here, and then as long as the naming convention is done properly, they will be on the same line item. And just on a quick glance, it's very obvious that our optimization yielded better temperatures. And of course, you can see a comparison on the remaining data also down here. Great. And to summarize, these are the two heatsinks that ColdStream created. For on the one side, you of course see these very organic shapes and structures that it made for a natural convection case, while with forced fan flow, it created a set of very interesting fins that work in harmony together to aid with the heat transfer. And to summarize the workflow I just exemplified, well, you can start off in ColdStream with a thermal analysis of an existing heatsink that you have. You then define this design freedom to redesign the heatsink, and at the end of it, you enjoy the benefits of thermal topology optimization that simply gives you a performance boost and roughly a 10% increase in temperature, 10% improvement in temperature performance, so a 10% reduction was observed. And so to summarize the benefits of using generative design with ColdStream, well, first and foremost, we shorten overall design cycle times. We see that over and over again, that while with classical engineering, a thermal design can take several months, ColdStream will reduce that to only a few weeks, while of course the performance is beyond human capabilities, because simply the structures that ColdStream has the potential to generate, a human could not draw those themselves. Meanwhile, this is all wrapped in a very nice automated workflow, so actually the amount of manual engineering time decreases significantly, and setting up a case in ColdStream, including CAD preparation, will take you less than an hour. And of course, it provides you a really great new type of design methodology to explore what is possible in heatsink design. All right, now we have time for a few questions. I hope you've been posting a few in the chat. If not, now of course is a great time to do so. So I have a few questions already here from the chat. The first one is, if I want a die-casted heatsink instead of a 3D printed one, can you design for this? Yeah, absolutely. So of course, for today's use cases, we explored the potential of 3D printing heatsinks, But as a reminder, we can account for milling, we can account for die casting, and even sheet metal forming. So you as a ColdStream user would have the freedom to constrain the manufacturing towards the capabilities that you desire. All right, next question is, can I input a target to make the most cost-effective heatsink? Yeah, that's a really good question. The answer to that is indirectly you can. So we have a target in ColdStream available called a relative volume minimization. And when you assign this to the design space, ColdStream will generate a heatsink that will perform to the thermal requirements you set, while trying to use as little material as possible. And of course, material savings, if you're talking about mass manufacturing, creating a really high volume, can yield cost savings. So indirectly, through the relative volume minimization, through making heat sinks with as little material as possible, you can minimize your costs. All right, next question I have is, for my LED module, I have a tight packaging space and limited room for the heatsink. Can ColdStream account for this? Yeah, absolutely. So of course we know it's common that in the LED world and lighting fixture world, you might have very limited packaging space, especially in the ceiling. And there, as long as you adopt your design space, which indicates how much volume does ColdStream have to create the heatsink, we can adopt to this. And so essentially the design space can be as complex as you want it to. It can be an asymmetrical shape, it can be cylindrical, it can really be as exotic as you would like to, and ColdStream will generate the heatsink within that. So especially for tight packaging spaces, we have a solution for that. Last question I have is, if the input heat flux changes, can you quickly see the impact on the heatsink temperature? Yeah, so as a reminder, with the thermal network that I showed you, if you, for example, are uncertain how strong of a LED you would like to include, and you know that the power, of course, would change depending on your LED selection, you can actually see what the resulting effect on the final temperature will be just via running a quick simulation, getting that thermal network and seeing the thermal resistance. And using that thermal network, you can actually very easily see how a change in heat input would affect the temperatures. And so ColdStream is a very useful thermal software in that regards too, to get a quick estimation on predicting such behaviors. All right, I think we are a little over time. I want to thank you all so much for joining today's webinar. The last thing that I want to leave you with is that you can actually try ColdStream for free right now if you go to our website, diabatix.com, and you can actually explore the 2 use cases that I've outlined today on the account that we have made available for you. And of course, if you would like to contact me directly, please don't hesitate to get in touch with me. Maybe we can have a short chat about how ColdStream could help you out with any of your thermal problems. And yeah, my contact details are right there, both my email and my phone call and my phone number. And yeah, just as a reminder, I will be in touch in the next few days with a copy of the recording of this webinar, as is standard with all of our webinars, so be on the lookout for that. Thank you once again for joining, and I hope to see you at the next one.